Okay, so we've already talked a little bit. We've seen it in the uniform case of how we do expected value in for at least one particular continuous distribution in the uniform, and we talked about how that involves the replacement of sums with integrals, and we're going to talk about that in more detail now. So okay, so x is going to be a random variable with a density. Then the way we take expectations in general is, as we talked about, we take integrals of the density. And in general, we're going to define this for a function of the random variable. The expectation of a function g of x is the integral over all possible values of x, which we can say from minus infinity to infinity, of the function g weighted by the density of x dx. Now, technically, the way that we have to define this, just like we did in the previous, in the initial case, is we have to break this up into positive and negative parts. So it's the integral of g plus minus the integral of g minus. Okay, this is where g plus x is the max of x and 0, g minus x is the max of minus x and 0. So it's the positive and negative parts. Very rarely in the distributions we end up talking about and the functions we'll talk about, is it necessary to actually break it up that way? A lot of times we can do it just all in one because we're dealing with well-behaved functions. But this is technically what we have to do, as we talked about earlier in the course, because of the possibility that one of these two pieces might be infinite and it could throw everything off. Okay. So the usual rules apply. What do I mean by that? If we have two random variables, x and y, and real numbers a and b, then we have linearity of expectation. So expectation of ax plus by plus constant c, this is an extra constant here, ABC, is a times the expectation of x plus b times the expectation of y plus c. The variance of x, no change there. That's, we can calculate that, expectation of x squared minus expectation of x quantity squared. Variance of ax plus by plus c. The extra c does not affect the variance. And this comes out as, well, let's be very careful about this. So this is equal to variance of ax plus by. This is equal to variance of ax plus variance of by plus 2 times the covariance of ax with by. And then we can take the constants out. So a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y. So now, y exactly, so these are exactly the same as the formulas for discrete random variables, no changes whatsoever. It's just how we calculate them that that changes. So covariance of x and y is expectation of xy minus product of the expectations. Okay. One thing we can do in the case where we have a non-negative random variable is we can compute the expectation in a particular way, if we'd like. What do I mean by that? So let's take the expectation of x. Since it's a non-negative random variable, we just integrate over the region 0 to infinity. And now here's where we have to get creative again. One thing we can do is we can rewrite x. Let me just write it here. A constant x. Remember how in the discrete case, we could write a constant in the discrete case, we could write an integer n as the sum from j equals 1 to n of a constant 1. Well, in the continuous case, what's the analog to that is a constant x can be expressed as the integral from 0 to x of 1, okay? And so that's exactly what we're going to do here, is we rewrite x as the integral from 0 to x dy, and then we have f of x dx. Okay. Now, what's troubling about this is that okay, so what's troubling about this for us right now is that the integral from 0 to x has this variable x in the limit of integration, which is going to cause us a little bit of difficulty. So now remember, what did we do in the discrete case? Well, we made this an unbounded sum, 1 to infinity, by defining an indicator variable, and the indicator variable was I sub n of j. Okay. And we can do the same exact thing in the infinite case. We take the integral from 0 to infinity of I sub x of y dy. And this is where I sub x of y is 1 if y is less than or equal to x and 0 otherwise. So it's integral 0 to infinity, integral 0 to infinity, indicator xy, f of x dx. Okay. So now what, I lost something. Indicator xy, f of x, dy dx. Okay. And now what we realize is, okay, let's try to switch the order of integration. Let's integrate by x with respect to x first and then y. And if we do that, what happens? Well, does that change anything? Well, the limits of integration don't depend on anything, so we can certainly do it. But how does that affect this piece here? Well, this here, when we're looking as a function of x, is going to be 1. So when we have, so here we have a fixed value of y, right, instead of a fixed value of x. So since y is fixed, this is going to be 1 as long as x is less than or equal to y, right? Hold on, let me. Sorry, this is now have to be looked at as a function of x and not y, right? And we're doing dx, right? And so this is going to be 1 provided x is greater than or equal to y, right? And so this now can be, we can put the limit back into the integral, but the way it comes in is from, we only have 1 for values bigger than y. So it's from y to infinity, f of x, dx, dy. And now what is that? Well, integral from y to infinity of the density, that's the probability that x is bigger than or equal to y. And we still have the integral from 0 to infinity dy. So we can calculate the expectation of x by integrating what are called the survival probabilities. So these are survival probabilities, meaning that it's that x survives past y, x is bigger than y. They're the inverse in some sense to the distribution function, which is the probability that x is less than or equal to y. However, less than or equal to an argument y. However, they're not exactly opposites because there's the overlap where the equality of y. And that's 0 in the case of a pure continuous random variable, but if we have masses in the distribution, that could prove to be an issue. Okay, so we have to be a little careful there. Using the same ideas, we can calculate the expectation of x squared. Integral x is 0 to infinity, x f of x dx, but remember, x squared is always bigger than or equal to 0, so we can utilize exactly what we had up above and say, well, this is equal to the probability that x squared is bigger than or equal to y dy. Well, what we can do now is we can then, whatever we do to one side, we do to the other. So x squared is bigger than y as long as x is bigger than or equal to square root of y. And if x is a random variable, right, and x is non-negative, x is going to be bigger than or equal to the positive square root, right? So we could still do this in the case where x was an arbitrary random variable. We would just have to take into account x being less than or equal to the negative square root, okay? Now, if we introduce a change of variables here, calling x square root of y, that means that y is equal to x squared and dy is equal to 2x dx. Then we do a change of variables and we go still from 0 to infinity. Of substituting dy, we have 2x dx. So 2x dx, probability x bigger than or equal to x. Okay. So anyway, these can be useful. I wouldn't say that these need to be memorized by any means, but there's certainly this is certainly worth knowing, I would say. This is certainly worth knowing and using when appropriate. But again, just seeing how once we have the tools at our disposal, we can continue to build upon them and to expand them. as we've been here. So that's expectation for continuous random variables.